Hello, students. Welcome. Today, we're going to do a complete revision of a very important chapter, Magnetic Effects of Electric Current. The idea is to go through it calmly, step by step, so that you feel absolutely confident for your exams. Shall we start?
Now I know many of you might be feeling a little nervous about this chapter. There are rules, there are diagrams, it can seem like a lot. But trust me on this. If we just make the fundamental concepts crystal clear, this chapter is actually very simple and very scoring. So don't worry. Let's make this easy together.
All right, so let's begin right at the beginning. Where did this whole idea come from? Well, it all started with one simple but revolutionary discovery, that electricity and magnetism are two sides of the same coin. They're connected, and the scientist who first discovered this link was Hans Christian Ørsted.
So what did Ørsted actually see? It was something surprisingly simple. Way back in 1820, he noticed that whenever an electric current was passed through a wire, a magnetic compass needle placed near it would suddenly move. It would get deflected. That's it. Such a simple observation, but it changed everything.
And from that one small observation, he drew a massive conclusion. He realized that an electric current must be producing a magnetic effect in the space around it. This, my dear students, is the fundamental idea of this entire chapter. So let's summarize this first part. An electric current produces a magnetic field. Simple.
Okay, so we know there's a magnetic field, but it's invisible, isn't it? So how can we possibly visualize it? How do we understand its direction and strength? Well, for that, we use a very clever concept called magnetic field lines.
Now, the first thing to remember is that magnetic field lines are, well, they're imaginary. They are not real lines. They're just a tool we use to represent the magnetic field on paper. The most important thing about them is this. The tangent drawn at any point on a field line gives you the exact direction of the magnetic field at that very point.
And you know, even though we call them imaginary, you can actually see their effect. Look at this. When you sprinkle tiny iron filings around a magnet, they don't just land anywhere. They automatically arrange themselves into this beautiful pattern. They are literally tracing out the magnetic field lines for us to see.
All right, let's quickly go over the properties of these field lines. This is a very common exam question. First, their direction. Outside the magnet, they always go from the North Pole to the South Pole. But inside the magnet, they travel from south back to north. This means they form continuous, closed curves. That's a key word. Second, and this is very important, they never intersect each other. Why? Because if they did, the compass would have to point in two directions at once, which is simply not possible. And finally, the strength. Where the lines are crowded together, the field is strong. Where they are far apart, the field is weak. So, in short, these properties tell us everything about the field.
Okay, so we've established that a current-carrying wire has a magnetic field. But what happens if we change the shape of the wire? Does the magnetic field pattern stay the same? The answer is no, it changes. So let's look at the three main shapes you need to know for your exam.
First up, the simplest case, a long straight conductor. As you can see in the diagram, the magnetic field lines are perfect concentric circles, with the wire right at the center. And notice how the circles get farther apart as you move away from the wire. What does that tell us? It tells us the magnetic field gets weaker.
Now, let's take that same wire and bend it into a circular loop. What happens now? Well, near the wire itself, the field lines are still circular. But look what happens towards the center of the loop. The field lines from every part of the loop start adding up, and they become nearly straight and parallel. This makes the magnetic field at the center very strong.
And that brings us to the solenoid. Now, what is a solenoid? It's simply a coil of wire with many circular turns, wrapped in the shape of a cylinder. And the most important thing to remember here is that its magnetic field looks almost identical to the magnetic field of a bar magnet. This is a very important comparison for your exam. But the real magic of a solenoid is what's happening inside it. The magnetic field inside a long solenoid is uniform. Now, what does the word uniform mean? It simply means the field has the same strength and the same direction at every single point inside. And how do we draw that? We show it with parallel, straight lines that are equally spaced. So to summarize this section, the shape of the conductor directly controls the pattern of the magnetic field.
Okay, we know the patterns, but how do we figure out the direction of the magnetic field? For that, we have a very simple rule, the right-hand thumb rule. I want you to do this with me right now. Take your right hand. Imagine you're holding the wire. Now, point your thumb in the direction the current is flowing. Got it? The direction in which your fingers are curling around the wire,
That is the direction of the magnetic field lines. It's that easy.
All right, let's take this one step further. We know a current creates its own magnetic field. But what happens if you take a current-carrying wire and place it inside another external magnetic field? Something very interesting happens. The wire experiences a force. It gets pushed. Now, to find the direction of this push or force, we need a different rule. And this new rule is Fleming's left-hand rule. Please pay close attention here. This time, take your left hand. Stretch out your thumb, your forefinger, and your middle finger so that they are all at right angles to each other, okay? Now, remember this. Your forefinger points in the direction of the magnetic field. Your middle finger points in the direction of the current. And your thumb will automatically point in the direction of the force or the motion. Now, this is where students often get confused. So let's pause and make this absolutely clear. When do you use which rule? It's simple. You use the right-hand thumb rule when you want to find the direction of the magnetic field created by a current. You use Fleming's left-hand rule when you want to find the direction of the force acting on a current-carrying wire. Right hand for the field, left hand for the force. Please remember this.
Just one more thing on this topic. When is this force the strongest? The force is at its absolute maximum when the direction of the current is at a right angle, that is, 90 degrees, to the direction of the magnetic field. And this simple fact is the basic principle behind every single electric motor. So, to summarize, a current in a magnetic field experiences a force. That is the key idea.
All right, let's bring all this theory back home. Literally, we're now going to talk about the domestic electric circuits in our houses. And when we talk about this, the most important word is safety.
So, the wiring in our homes typically has three main wires. First, there's the live wire, which usually has red insulation. This is the one that brings in the current at a high potential of 220 volts. Then you have the neutral wire with black insulation. This one is at 0 volts, and it's there to complete the circuit. And finally, the most important one for safety, the earth wire, which has green insulation. It protects us from electric shocks.
Now, what can go wrong? There are two main dangers: short-circuiting and overloading. A short circuit is when the live wire and the neutral wire touch each other directly. This causes the current to suddenly become very, very large. Overloading is something we've probably all done. It's when you connect too many heavy appliances to just one socket. So how do we protect our homes from these dangers? We use a simple safety device called a fuse. A fuse is just a special wire that melts and breaks the circuit if the current becomes too high. So, to summarize, for safety at home, we rely on proper wiring and devices like the fuse.
So there we have it. We've gone through the entire chapter. Now for the final part, let's talk strategy. How can you make sure you get full marks on any question from this chapter in your exam?
Number 1, practice your diagrams. You should be able to draw the field lines for a bar magnet, a straight wire, and a solenoid cleanly. Number 2, master the rules. Know exactly when to use your right hand and when to use your left hand. Don't get them mixed up. Number 3, when you get a why question, like why don't field lines intersect, always start your answer by stating the rule or the property first. And finally, please avoid the common mistakes. Don't mix up the rules and don't get the wire colors wrong.
And that's it. We've covered every key concept from start to finish. You have successfully revised the entire chapter. The only thing left to do now is practice. So stay calm, practice well, and I am sure you will do great. All the very best for your exams.